Application example. We will use the following example to clearly demonstrate how to wire and configure an SR745 relay. In our example, we will consider the application of a step-down distribution transformer located at the end of a transmission line. We will be stepping down the voltage from transmission levels of 220 kilovolts to the required distribution level of 69 kilovolts. The system that the transformer is installed in is 60 Hz with an ABC phase rotation. The transformer that we will be using is a YD30 with a power rating of 100 MVA or megavars. This means that the primary or high winding of the transformer is configured as a Y or star, and the secondary or low winding is configured as a delta with a 30-degree phase shift between the windings. To calculate the nominal current for each winding, we will use the following formula. The nominal current is equal to the transformer power rating divided by √3 times the nominal voltage. For the high voltage winding, this will be 100 MVA divided by √3 times 220 kilovolts, or 262.43 amps. For the low voltage winding, it will be 100 MVA divided by √3 times 69 kilovolts, or 836.73 amps. Our transformer is also equipped with an on-load tap changer located on the low or secondary winding. There are a total of 33 tap positions ranging from 61 to 77 kilovolts in 0.5 kilovolt increments. The resistance increment per tap is 30 ohms. When selecting the CTs for our transformer, we want to make sure that the I nominal falls between 50 and 100% of the CT primary. The closer nominal current matches the CT primary, the more accurate the current metering will be. As we cannot match the calculated nominal currents exactly to an available CT primary, we will use 500 to 5 CTs on the high voltage winding and 1000 to 5 CTs on the low voltage winding. The relay will internally calculate the mismatch in the CTs and will compensate for it in the percent differential calculations. It is very important that the CTs being used for the transformer are tested for saturation and accuracy. In order to accurately set the differential settings, we need to know the minimum and maximum saturation points, as well as the percent accuracy of the CT metering. The CTs that we've selected for our system have been tested, and the results are as follows. The winding 1 CTs have tested with a tolerance or percent error of 10%. The CTs will start to saturate or begin to show nonlinear operation at 2000 amps primary and will saturate to a total of 65%. The winding 2 CTs also tested with a tolerance of 10%. The CTs will start to saturate at 4500 amps and will reach a total saturation at 50%. The wiring diagram will provide the additional information required for the relay's configuration. The winding 1 CT primary will be 500 amps with a secondary of 5 amps. The secondary windings will have a primary of 1000 amps and a secondary of 5 amps. The G12 ground will be connected using a zero-sequence CT with a 250 amp primary and a 5 amp secondary. A single voltage transformer will be connected across the winding 2 A and B phases with a ratio of 600 to 1. The on-load tap changer will be wired into terminals A3 and A4. The trip 2 output will be wired as our trip relay, while auxiliary 8 will be wired as an alarm contact, feeding our PLC. We will also use logic input 1 as a blocking signal for the percent differential element. When asserted, the differential element will be disabled, allowing us to perform transformer testing and commissioning. For example, if we use a common trip output and wish to test only the overcurrent element, we can use the input to disable the differential so that only the overcurrent will cause operation of the trip contact. This section will provide an example of programming a relay using the Vista setup program. The first step in using the setup program is to configure the communications to allow us to talk to the relay. We will do this by selecting the Device Setup button located above the online window on the left side of the screen. In the window that appears, you will see the panel on the left-hand side showing the text, "Please add a site." This indicates that no sites or devices have been set up for communications. First, we need to add the site that will contain the relay. Press the Add Site button found at the top of the window. A new site will be added with the default name New Site 1. To change the name of the site, click on the Site Name field and type in a new name. Next, we will add all of the devices that we want to be found in that site. Highlight our site by clicking on it and press the Add Device button. Two things should now have occurred. The name of our site would have changed, and a new device will be added to the site with a default name, New Device 1. We now need to configure that newly created device. In the panel on the right, click on the Device Name field. Type in a new name that describes that relay. Open the pull-down menu. Because we are configuring to communicate with an RS-232 serial cable, we will select Serial from the menu. Several new fields will appear in the area below. The Modbus slave address is used to identify specific devices for communicating on the network. When communicating through the front port, there is only one device on the network. Therefore, there is no risk of communicating with the wrong device. For this reason, we can leave the Modbus slave address to the default of 1. In the COM port field, select the communication port of your computer that the serial cable is connected to. The COM port that we are using is COM1. Therefore, we will leave this at the default. The baud rate is user programmable. In this example, we will set it to 19,200. The order code and firmware version of your UR can be read from the relay itself to fill in the last two fields. Press the Read Order Code button. Press the OK button. Basic Setup. The following section will provide simple instructions for using the Vista 745 setup program to configure the SR745 relay. Once the device setup has been completed, you will see the name of the site you have created in the device window. By opening this menu, you will see the name of the device that was set up for communications. Opening this menu further, you will see the menu structure for the relay itself. This is one of two methods that can be used to view the settings and actual values that are present in the relay. By double-clicking on the settings, and then the 745 setup, you will see the available settings for the basic operations of the relay. By double-clicking on a settings menu, you will see the specific settings for that function. For example, by double-clicking on Passcode, you will be able to see the settings for enabling and disabling the passcode protection. The second method for viewing the settings in the relay is to click on the Setpoints drop-down menu located at the top of the Vista 745 setup window. This will show a list of all settings pages within the relay. Please note that the grouping under the Setpoint drop menu matches the structure of the Setpoint pages found in the relay. If you familiarize yourself with the menu structure by using the PC program or the keypad, the transition to the other interface will be very simple. Select 745 Setup. A window will open that displays all submenus, including passcode. Clicking on the Passcode tab allows you to view the settings for enabling and disabling the software security. Customizing the appearance of the setup program can make it easier to navigate the settings of the relay. For instance, the settings windows can be resized. For this training CD, we will be using the drop-down menus located at the top of the window, so we can close or shrink the file and device windows to allow a larger viewing area for the settings. Double-clicking on the border of the settings window will size it to the available viewing area. We will now program the basic relay set points required to protect a transformer. The values we will be using are intended only as an example. Let's start by entering some of the basic settings required for the 745 relay to operate properly. The first is the passcode. This setting, in combination with the hardware setpoint access switch mentioned earlier, provides security for the relay and its settings. Select 745 Setup from the Setpoint menu, and then the Passcode tab. Setpoint access will let you know if the relay allows setpoints to be written to the device. If the access states Read Only, then the device has been passcode protected. All relays are defaulted from the factory with no passcode protection. To enable the passcode protection, click on the Change Passcode button and enter your passcode twice. You can now select the Restrict Access button. If you forget your passcode, there is an encrypted passcode provided. Please record this encrypted passcode and call GE Multilin Technical Support for assistance. If you wish to disable the passcode protection, first you must enable write access to the relay. Then change the passcode to 0. This will remove any passcode protection from the relay. To ensure that the recorded events and waveform files are time and date stamped correctly, select the Real-Time Clock tab to set the date and time. You can choose to synchronize the relay date and time to your computer using the Sync Relay to Computer button, or you can store the date and time manually by entering the information and selecting the Set Manual Date and Time button. If more accurate timestamping is important to your application, it is possible to connect the SR745 to an iRig-B generator. You must select the iRig-B type as either DC shift or amplitude modulation. If you have a relay that has the factory default settings, you will see that there is a self-test warning present on the display indicating that the set points have not been programmed. To prevent the relay from being installed into a system with the default settings, there is an installation setting that must be programmed in order to enable the protection and control elements of the relay. Select the Installation tab and change the SR745 Setpoint setting to Programmed. When you have changed a setting in the PC program, the new setting does not take effect until it has been saved to the relay. Always click on the Save button after making the necessary changes to the settings. Any latched trip or alarm within the relay can be reset by either using the Reset button on the front panel or by using a remote reset signal wired into the relay. In order to use the remote reset functionality, a logic input must be assigned within the relay. Select the Resetting tab to access these set points. The local reset block set point is used to disable the front panel reset button so that all latched elements must be reset using the remote signal. We will not assign an input to this parameter. The remote reset signal will allow us to assign a logic input that will reset any latched element in the relay. We will program this as logic input 3. Using these settings, we can now reset any latched element using either the front panel reset key or by asserting logic input 3. System Setup. This section will illustrate how to program the relay to properly detect current and voltage levels. In order to properly meter and provide protection, the relay must know the specifics of the system it is connected to and how it is connected to the system. The first thing that we must do is let the relay know the type of transformer that is being protected. Select the Setpoint drop-down menu and then System Setup and Transformer. The first two settings will let the relay know the frequency and phase rotation for the power system. We will leave these settings as they are, as we will be protecting a 60 Hz system with an ABC phase rotation. The third setting, Transformer Type, will indicate the wiring configuration and phase shift of the transformer that the SR745 will be protecting. This setting is very important as the phase angle of the winding 1 and winding 2 currents will be used in the differential calculations. If this set point is not accurate, then the relay may expect to see levels of phase shift that will not be present in the system. When you select this set point, a complete list of all transformer types available will appear. If you are using a 2-winding transformer, the 3-winding transformer options will automatically be removed from this list. As the transformer in our example is a Y delta 30, we will select the YD30 transformer from the list. This means that the primary winding of the transformer is configured as a Y, and the secondary is a delta, with a 30-degree phase shift between the windings. Select Save and close the window. We now need to program the settings for each of the individual windings. Select System Setup and the windings from the Setpoint menu. You will see tabs available for 3 windings, but by selecting the Winding 3 tab, we can see that no settings are available, as we have already programmed the relay to protect a 2-winding transformer. No system or protection settings for the 3rd winding will be available when programming this relay. Select the Winding 1 tab to view all the available settings. From the information provided in our example, we know that the rated voltage for the high side of our transformer is 220 kilovolts. To program this value, click anywhere in the Setpoint field. On the right-hand side of the field, you will see 3 arrows. Clicking on the smaller arrows will increment and decrement the setting in small steps. Selecting the larger arrow will open up a window that looks similar to a calculator keypad. Enter 220 and then select Accept. The rated load of this transformer is 100 MVA, and this is constant for all windings. Enter 100 MVA as the W1 rated load. This value will be used as a reference for the transformer overload protection. We know from our wiring diagram that 500 to 5 CTs have been selected for the high side, so we will program the W1 phase CT primary as 500. The ground CT primary setpoint will vary depending on the connection. If a residual ground connection has been used, then this setpoint must match the setting for the phase CT primary. As we have opted to use a zero-sequence CT with a ratio of 250 to 5, the W1 ground CT primary must be set to 250. The three-phase resistance is only used for the optional loss of life element. As we will not be using this element, we can leave the setpoint programmed to its default value. Select the Winding 2 tab to view the settings for the low voltage winding. We will program the rated voltage as 69 kilovolts with a CT primary of 1000 amps. The rated load will remain the same at 100 MVA. You will notice that there is no ground CT primary setpoint available with this winding. This is due to the lack of a neutral or ground conductor on the delta side of our transformer. Only windings that have been configured as a Y or zigzag will have ground CT settings available. Select Save to store the set points to the relay and close this window. Our transformer has been equipped with an on-load tap changer. If this tap changer is connected to the SR745, then the relay can dynamically adjust the calculated CT mismatch factor based on the actual transformer voltage ratio. As the load or generation shifts, the transformer will automatically adjust its ratio to allow transmission or distribution voltage levels to remain constant. Monitoring the position of the tap changer allows for greater sensitivity when programming the percent differential element. To program the tap changer setpoints, select System Setup and On-Load Tap Changer from the Setpoint menu. Our tap changer is on the low voltage winding, so we will select Winding 2 for the first setpoint. The tap changer has 33 positions with a minimum voltage of 61 kilovolts. The voltage increment per tap is 0.5 kilovolts with a resistance increment of 30 ohms. Once these set points have been programmed, select Save. The 745 will now monitor the on-load tap changer input for resistance. As the resistance to this input changes, the relay will be able to calculate which tap position the transformer is at and accurately determine the voltage ratio being used. The final system settings that we need to program are for the voltage input to the relay. Select System Setup and Voltage Input from the Setpoint menu. The Voltage Sensing setpoint will enable the voltage inputs to the relay. This voltage input is an optional input and is not required for basic transformer differential protection. It is required, however, for energy and power calculations, as well as to provide voltage frequency protection and allow energization detection by voltage level. If a VT is not connected, this setpoint should be left as disabled. For our application, we will need to change it to enabled. The voltage input parameter setpoint will let the relay know which phase or phases the VT is connected to. The VT can be wired across any two phases or from any phase to neutral. We will program this as W2 VAB, as our VT is connected across the A and B phases of winding 2. We must now calculate the nominal Vt secondary voltage. We will do this by dividing the nominal system phase-to-phase voltage by the ratio of the Vt installed. We know that the nominal phase-to-phase voltage on the low voltage winding of the transformer is 69 kilovolts, and that the Vt ratio is 600 to 1, giving us a nominal secondary voltage of 115 volts. Finally, we must enter the Vt ratio, already determined to be 600 to 1. Save these settings to the relay and close all windows. Our relay has now been programmed to accept voltage, current, and tap changer inputs from our transformer. We are able to accurately meter system values as well as calculate power, energy, and harmonic content of the system. Now that we've programmed the basic set points that the relay needs to monitor the system, let's take a minute to look at where the relay displays the metered and calculated values from the system. Select the Actual drop-down. The subheadings in this menu contain all metered values in the system, the current status of inputs and outputs, as well as historical data, such as the event recorder and oscillography files. The Status menu will contain the status of any active targets or elements, as well as the status for all contact and virtual inputs and outputs. There is also a tab available for any active self-test errors. Any metered or calculated values from the relay can be found under the Metering subheading. There are tabs available for displaying real-time currents, voltages, and frequency, as well as the calculated power, energy, and demand values. The metered analog input values will also be available here if they've been programmed. Please note that the voltage, power, and energy metering will only be visible if a voltage transformer has been programmed. One of the strongest tools available with this relay is its event recorder. The event recorder runs constantly, recording the system and relay status whenever an event occurs. Information such as current amplitude and angle, voltage levels, ambient temperature, and harmonic contents will be recorded for every event. The event recorder can store up to 128 events. If the number of events exceeds 128, the oldest events will be replaced with new events. This information is non-volatile and will not be lost if the power to the relay is removed. Let's take a closer look at how to access the event information. Select the event recorder from the Actual drop-down menu. At the top of the event window, you will see a list of all events that have occurred in the relay. This list will include the time, date, and cause of the event. If you scroll down, you will see a drop-down bar for selecting the specific event number you wish to look at. We will choose event number 223, listed above as On Self-Test Relay. Scroll further down the page. Now we can see the metered information from when the event occurred. This is a snapshot of the exact values seen by the relay when the event occurred. There are two buttons on the right side of the screen. The Clear Events button will reset the event recorder, deleting all event data from the relay. We will select the Save Event Data button so that we can store a soft copy of the events for future analysis. You will be prompted to save either all of the events in the event record or only the events that have been selected. We will choose All. It is important when naming the event file that the extension remains as CSV. This will allow the events to be opened in Microsoft Excel. You now have a permanent copy of the events and can reset or clear the events in the relay. We will do this by simply selecting the Clear Events button. When the clear is complete, no events will be listed in the event recorder. Product information will provide hardware and software information specific to this relay. This information includes serial number, firmware or software revision, and the order code of the relay. There is also a calibration tab that will record the most recent date the relay was factory calibrated. The trending is similar to the Waveform Capture, providing historical system information. The difference is that the trending file can be programmed to capture only the analog values that are required. Data will be captured at time intervals determined by user programmable set points. The captured information is stored in volatile memory and will be lost if control power is removed from the relay. The Waveform Capture is used to capture and analyze waveforms captured from the system at the time of events. This will be discussed in greater detail under the Output section of this CD. The front panel will open up an HMI display, allowing a visual representation of the front of the relay to be displayed within the PC program. This is useful when communicating to a relay that is not near your computer. The differential element. Differential protection is the most important protection element for transformer protection. It is only in very rare and specialized conditions, such as testing and commissioning, when the differential element will be disabled. In this section, we will examine the settings for the differential element, as well as associated differential inhibit functions, such as second and fifth harmonic inhibits. We will also program the relay to be able to detect the energization of the transformer. Percent differential settings. As the main transformer protection, it is important that the percent differential element is programmed as accurately as possible. To access the differential settings, select Elements and Differential from the Setpoint menu. You will now see tabs available for all the differential and inhibit functions of the SR745. Select the Differential tab. The percent differential function is factory defaulted to Enabled and should only be disabled during special conditions such as transformer testing. The percent differential target set point determines how any operation of this element will display on the screen of the relay. A setting of self-reset indicates that a differential message will appear on the screen of the relay for as long as the differential condition exists and will be removed from the screen automatically when the differential condition is no longer present in the system. A setting of latched will cause the differential message to be latched onto the display and will require a manual reset once the differential condition is no longer present. Programming this message to none will mean that no differential message is ever displayed, even when a differential condition is actively present. As discussed in the theory section of this course, the minimum pickup for the percent differential element should be set to the amount of differential current that can be present in the system due to CT inaccuracies. We can calculate this by multiplying the nominal current by the total percent error of the CTs. In our case, the total tolerance is 10% for winding 1 plus 10% for winding 2 for a total of 20%. Our I nominal will be 500 amps for a total of 100 amps or 0.2 times CT. Our slope 1 should be set to the total CT percent error, plus a recommended buffer of 5 to 10%. We can use the smaller buffer of 5% because we have connected the on-load tap changer of the transformer to our relay. Our total percent error for winding 1 and winding 2 is 20%, so we will use a setting of 25%. The breakpoint of our differential slope is intended to represent the point any one of the CT's secondary current will begin to show nonlinear operation. It will be programmed to the minimum amount of restraint current required to cause any of the CTs to start to saturate. This value is generally derived from testing of the CTs for saturation. For our application, we will use a value of 4 times CT. This means that when the restraint current measured by the relay reaches 2000 amps, we will enter the area defined by the second slope of our two-slope curve. The second slope of the differential element is designed to protect against false trips during external fault conditions. Heavy through-fault currents caused by external faults can cause saturation of the CTs and therefore high levels of differential. As we do not want to operate due to the saturation caused by external faults, the second slope is set very high so that the differential element will not pick up. We will program the percent differential slope 2 setting to the maximum percentage of saturation that any of the CTs will see. We determine this value by testing the CTs to see what percentage of the input signal will be present on the secondary of the CT during maximum fault conditions. For example, if our maximum fault current is 5000 amps, but due to saturation the secondary of the CT only outputs 2000 amps, we know that only 40% of the signal is seen, or 60% saturation has occurred. We know from testing that under maximum fault conditions, the winding 1 CTs will see a total of 65% saturation, while the winding 2 CTs will see a total saturation of 50%. So we will program the slope 2 as 65%. We know from our system requirements that a remote blocking signal is required for the differential element. The final setting, percent differential block, allows us to assign a logic input as the blocking signal. We will set this set point to logic input 1. Whenever a logic input has been assigned to a function within the relay, it is important to make sure that the input has been enabled in the programming of the relay. To enable the input, select Logic Inputs and Logic Inputs from the Setpoint menu. This will open a window that allows the function, name, and asserted state of the logic input to be programmed. Change the logic input function of logic input 1 to enabled. Enter the name of percent differential. This will now be displayed whenever the logic input 1 is asserted. If the target has been set to self-reset, then this message will only be present while the input is asserted. If programmed to latched, then the message will remain on the screen until manually reset. We will leave this as self-resetting. The final set point is the asserted state. If programmed to closed, then the logic input will be asserted when the contact input is shorted. If selected as open, then the logic input will assert when the contact is open. We want the contact to be closed when asserted, so we will leave this set point as closed. As mentioned before, remote blocking of the differential element using a logic input is a rare condition, generally performed only when testing or commissioning of the transformer. Select Save and close the logic input window. The basic set points for our differential protection have been set, and we can proceed with the programming of the inhibit functions of the relay. Energization inhibit. Magnetizing inrush occurs when a transformer is energized. Since inrush current flows only in the energized winding, differential current results. In order to protect against nuisance tripping of the transformer during energization, the SR745 provides an energization inhibit element. Typical inrush currents contain a substantial amount of harmonics. This is a harmonic inhibit function which will be enabled when the 745 detects that the transformer is energizing and remains active for the duration of the energization inhibit timer. Select the Energization Inhibit tab to access the set points for this element. We will enable this element by changing the function setting to enabled. The energization inhibit parameters will determine if the relay considers only the second harmonic levels or both the second and fifth. By setting this to second and fifth, the relay will use the sum of the second and fifth harmonics present in the system and calculate what percent of the fundamental these harmonic levels represent. The relay will then compare the calculated percentage to the energization inhibit level set point. For most transformers, the second harmonic levels are high enough during inrush and energization conditions, so we will set this to the second harmonic set point. As this inhibit function is a phase per phase element, it will calculate the harmonic content in phase A and use that value to block only differential conditions seen on phase A. The harmonic levels for phase B will be measured and used to block only differential conditions seen on phase B, and the same is true for phase C. Because of this, it is possible to have differential conditions seen on phase A blocked due to high harmonic levels seen on phase A. But if the harmonic levels on phases B and C are low, the differential element can still operate based on high levels of differentials seen on these phases. Enabling the harmonic averaging will average the levels of second harmonic present on all three phases and use this as the level of harmonics to calculate the percentage of fundamental for all three phases. If high levels of harmonics are seen on one or two phases during energization, but not seen on the third, the relay will average all three metered values of harmonics and then block or not block the differential for all three phases based on this value. We will be leaving this element disabled, as we want to have the energization inhibit to operate as a phase per phase element. Next, we must program the level of second harmonic that must be present in the system in order to inhibit the percent differential element. This set point is programmed as a percent of the fundamental frequency. 20% of the fundamental is an industry-accepted level for this set point, and is the value that we will use. The last set point that we must program for the energization inhibit is the duration timer. This timer will be the amount of time the energization inhibit element will be active after the 745 has detected the start of energization. We will use the default value of 100 milliseconds for this set point, as we expect both windings of the transformer to be fully energized within that time period. 100 milliseconds after the start of the energization, the energization inhibit element will be disabled, and the differential will be allowed to operate regardless of the levels of second harmonics in the system. Energization Sensing. In order for the SR745 to enable the energization inhibit, it must be able to determine when the transformer is de-energized or is initiating its energization. The relay will always detect the energization of the transformer based on the level of current in the system. If the current rises above the programmable set point, the transformer will be considered energized. The detection of de-energization, however, can be programmed to be based on the level of current, voltage, or the status of a contact input from the transformer breaker 52B contact. Select the Energization Sensing tab. With Energization Sensing by current enabled, all currents dropping below the minimum energization current indicates a de-energization of the transformer, while any current exceeding this set point will be considered energized. This is the least reliable method of detecting energization, as an energized and unloaded transformer will be detected as de-energized due to the low levels of current. Selecting the Energization Sensing by voltage will still use the current level to detect the energization, but will look only at the voltage level to detect the de-energization. If the voltage level drops below the minimum energization voltage set point, then the transformer will be considered de-energized, regardless of the current level. If the breakers are open signal is programmed, the relay will again use the current level to detect the energization, while using the closed signal from the breaker 52B contact to determine the de-energization of the transformer. For our application, we will enable the Energization Sensing by voltage and disable the current and breakers are open signal. We will use a minimum voltage level of 80% of Vt and leave the minimum energization current at 0.1 times Ct. With this programming, the SR745 will detect the energization of the transformer when all 6 winding 1 and winding 2 currents exceed 10% of the Ct primary, and the transformer will remain energized until the relay detects that the voltage has dropped below 80% of the nominal secondary voltage set point. It is important in this application to make sure that the Vt is connected on the transformer side of the breaker, so that the voltage levels will drop when the breaker is opened. Fifth Harmonic Inhibit. During overexcitation of the transformer, high levels of fifth harmonic currents are present and can cause operation of the differential element. The SR745 also provides a harmonic inhibit that allows inhibiting the percent differential element during intentional overexcitation of the transformer. Select the 5th Harmonic Inhibit tab. We will enable this element. The Harmonic Averaging Setpoint will operate the same way as for the Energization Inhibit, allowing the harmonic content in all 3 phases to be averaged, and then the average value will be compared to the percent of fundamental setpoint to determine if all 3 phases should be blocked. We will again leave this setpoint as disabled, allowing the inhibit to operate as a phase-per-phase element. 10% of fundamental is an industry-accepted level for this inhibit and will be used in our application. Instantaneous Differential. In addition to the 2-slope percent differential element, the SR745 also offers an instantaneous differential element that will operate without the restrictions of the harmonic inhibit or restraint current levels. This element will be used for situations where extremely high levels of differential are present, and protecting the transformer from damage becomes more important than the stability of the system. Select Elements and Instantaneous Differential from the Setpoint menu. We must first enable the element by changing the instantaneous differential function to Enabled. We will program the target to Latched, forcing the instantaneous differential message to be displayed on the screen of the relay until it is manually reset by the operator. The pickup level for the instantaneous element is programmed as a multiple of the winding 1 CT, as opposed to a percentage of differential current. We will program this to 7 times CT. This will cause the instantaneous differential element to operate if the actual value of differential current reaches 7 times the winding 1 CT, or at 3500 amps. Phase overcurrent. In addition to the primary differential protection, the 745 also provides a number of secondary protection elements, such as the phase overcurrent. Select Elements and Phase Overcurrent from the Setpoint menu. You will see 1-phase time overcurrent and 2-phase instantaneous overcurrent tabs available for each winding. As mentioned earlier, the settings for the winding 3 overcurrent elements will not be available as we have programmed the relay to protect a 2-winding transformer. We will be using the timed overcurrent elements as well as a single instantaneous overcurrent for both winding 1 and winding 2. Select the winding 1 phase time overcurrent tab to begin programming. We will enable this element with a latched target, requiring any operation to be manually reset. The pickup level should be set to a value larger than the maximum overload current rating of the transformer. Since our CTs have been selected such that they are higher than the normal operating current of the transformer, as such, the setting of 1.2 times CT is recommended for this element. There are a number of overcurrent curves available for the timed overcurrent element, allowing for coordination with other devices in the system. As we are not using coordination in our example, we will use the extremely inverse curve, as it allows for rapid tripping under higher fault currents. The curve multiplier setpoint allows the trip times of the element to be changed without changing the shape of the curve. It will essentially shift the overcurrent curve along the time axis. We will leave this as 1 as the trip times provided by the extremely inverse curve meet our system requirements. The reset setting determines how the TOC will reset after the overcurrent condition has been removed. A setting of linear is used when coordinating with electromechanical devices, as it provides a timed resetting of the element similar to the resetting of the electromechanical induction disk. We will select the instantaneous reset, which will reset the overcurrent element as soon as the overcurrent condition is removed. We do not require a blocking signal for this element, so the TOC block setpoint will be left disabled. Select the Winding 2 Phase Time Overcurrent tab to program the TOC element for the low voltage winding. We will use the same settings that were programmed for the winding 1 protection. Enable the element as latched and program a pickup level of 1.2 times CT using an extremely inverse curve and a multiplier of 1. Select the Winding 1 Instantaneous Overcurrent tab. This element is used to instantaneously trip the transformer in the event that fault currents are high enough that protecting the transformer from damage becomes more important than the coordination of the system. We will enable this as a latched element. The pickup level for this element should be set higher than the maximum through fault current of the transformer. For our application, we will use a level of 10 times CT. The typical delay for this element is 0 milliseconds, as we want to have the transformer removed from the system as quickly as possible to avoid damage. We will again not use any blocking signals. Select the Winding 2 Instantaneous Overcurrent tab and program the settings the same as for the Winding 1 element. Enable the element as latched using a pickup of 10 times CT and 0 delay. Ground Overcurrent. The final protection elements that we will be using are the ground timed and instantaneous overcurrent elements. Select Elements and Ground Overcurrent from the Setpoint menu. You will notice that only the settings for the Winding 1 ground protection are available. This is because we have programmed the relay to protect a 2-winding Y-delta transformer. Only the Y side of the transformer will have a ground 0 neutral leg available. Select the Winding 1 Ground Time Overcurrent tab. This element will be enabled and programmed as latched. A fault analysis will provide an appropriate level for the pickup of this element. As we are using a zero-sequence CT, our setting can be set low due to the accuracy of the CT. We will be using a set point of 0.2 times CT. With our 250 to 5 CT, that will represent a ground fault current of 50 amps. We will use the same extremely inverse curve that was used for the phase overcurrent protection with a multiplier of 1. Our reset rate will be programmed as instantaneous, resetting the element as soon as the fault current has been removed. Select the Winding 1 Ground Instantaneous element. This element will remove the transformer from the system if the ground fault current is high enough to cause immediate damage to the transformer. We will again enable and latch this element. The pickup level will be programmed as 10 times CT, or 2500 amps. A delay of 0 milliseconds will be used, as any delay at this level of fault current will increase the chance of damaging the transformer. Output contacts. The output contacts of the 745 relay are not assigned under the individual protection elements. Instead, the elements will raise an internal flag, and this flag can then be assigned to an output contact using the flex logic provided with the relay. In order to better comprehend how flex logic is used in the programming of the output contacts, please review the flex logic movie found under the Theory section of this CD. A strong understanding of flex logic gates and equations is essential when programming the relay. Select Outputs and Output Relays from the Setting menu. You will see that tabs are available for all 8 programmable output contacts. Please note that the self-test relay does not have any user-programmable settings, as it will always operate as fail-safe and will only operate when the relay issues an internal self-test error. The Relay 1 tab will provide the settings for the solid-state contact. As we will not be using this contact in our system, we must select the Relay 2 tab. This will open the settings for the first mechanical output contact. We will be using this contact as our trip contact, so we must first program the name as trip and make sure that the output type has been selected as trip. The operation of the relay will be programmed as self-resetting, so that when the trip signal has been removed, the relay will revert to its non-operated state. We must now program the flex logic equation that will cause this output contact to operate. First, we must decide on the elements that we wish to cause a trip. The elements that we have programmed are as follows: percent differential, instantaneous differential, winding 1 phase time overcurrent, winding 1 phase instantaneous overcurrent, winding 2 phase time overcurrent, winding 2 phase instantaneous overcurrent, winding 1 ground time overcurrent, and winding 1 ground instantaneous overcurrent. Let's take a look at the logic that we'll be using. As mentioned in the Flex Logic Theory section, the logic equation is made up from combining inputs and gates. The inputs for our equation will be the elements that we have programmed. Because we want the output contact to operate if any or all of the inputs become active, we will be using an OR gate. For the inputs that we have identified, we will need an 8-input OR gate. To simplify the logic, there are a number of different ways that we can program the inputs. For example, we can combine all of the winding 1 overcurrent elements into a single input, any winding 1 overcurrent operate. All winding 2 overcurrent elements can similarly be combined into any winding 2 overcurrent operate. Our logic will then look like this. Now we need to take this logic and program it into our output contact flex logic. When reading the programmed logic, the 745 will start with the first line and read down until it reaches the end command. It is expecting to see the inputs listed first and then a gate to perform the logic. When we program the flex logic, we need to enter in all of the inputs and then use a gate with the appropriate number of inputs to tie them all together. First, we will enter all of the inputs. Starting with the first line, enter the following parameters. Percent differential operate. Instantaneous differential operate. Any winding 1 overcurrent operate. And any winding 2 overcurrent operate. You will notice that there are both operate and pickup options available for these elements. The pickup will raise a flag as soon as the element picks up, while the operate will raise the flag only when the element has timed out and has operated. For example, if we program the logic to include any winding 1 overcurrent pickup, a trip will occur as soon as the time overcurrent element detects the overcurrent condition, acting as an instantaneous element. We need to program it to any winding 1 overcurrent operate so that the trip contact will only operate after the element has picked up, timed out, and then operated. We now need to program the gate. We know we need a 4-input OR gate, so the 5th line will be programmed to 4-input OR. The last line will be left as the end command. Our relay is now programmed to cause a trip if any of the programmed elements operate. If more elements are required in the future, simply insert flex logic lines before the OR gate and change the OR gate to reflect the appropriate number of inputs. If flex logic is ever entered that contains gates not appropriate for the number of inputs provided, the relay will issue a flex logic self-test error, alerting the programmer to the programming error. The Waveform Capture is an invaluable troubleshooting tool provided with the relay. It will capture an oscillography file whenever a system event is recorded by the relay. These waveforms show the current, voltage, and digital waveforms for before, during, and after the trip. The waveforms are stored in volatile memory, so any loss of control power will cause the information to be lost. Waveforms should be stored prior to removing the relay from the system for maintenance. The waveform capture can be programmed to be triggered from a number of different internal and external sources using flex logic. To access the waveform setpoints, select Outputs and Trace Memory from the Setpoint menu. A window will open similar to the one seen when programming the output contacts. This window allows relay elements, inputs, and outputs to be programmed with flex logic to cause the trigger of the waveform capture. Before we program the triggers, we need to decide how much of the waveform will show pre-trip data and how much will show post-trip data. The number of pre-trigger cycles setpoints will allow you to determine how many cycles of waveform will be before the trigger or fault. For our application, we want to see more of what happened before the fault, allowing more information for troubleshooting. Of the available 15 cycles of data, we will select 12 cycles to be pre-trigger. We must now determine what element of the relay we will be using to trigger a waveform. Similar to the programming of the trip output contact, we want to use the percent differential, instantaneous differential, phase overcurrent, and ground overcurrent elements. We will start by entering in all of the elements, one per line. They will be programmed as follows: percent differential operate, instantaneous differential operate, any winding 1 overcurrent operate, and any winding 2 overcurrent operate. We want the waveform to be triggered if any of these elements operate, so we will use a 4-input OR gate for the next line. Our waveform capture will now capture a waveform whenever any of these relay elements operate. To access the waveform capture, select Waveform Capture from the Actual drop-down menu. In this window, you will see the total number of waveform captures that are currently stored in the relay, as well as a drop-down tab for selecting which waveform you wish to view. There are also buttons available to manually trigger a waveform, to clear or erase the waveforms, to save the waveform to a file, or to open a waveform that was previously saved. As we currently do not have any waveforms present in our relay, we will select the Trigger Waveform button. You will see the total triggers increase to 1. To the right of the Trigger Waveform button, you will see a button for launching the viewer. Click this button to view the selected waveform. When the viewer opens, you will see the waveforms displayed in the bottom right-hand window. This window operates very much like an oscilloscope. There are 2 cursors, colored blue and green, that can be moved horizontally along the waveforms. The window to the left of the waveform will display the metered values at the position of the cursors. You can select to view either or both of the cursors, as well as the delta value between them by selecting any combination of the 3 buttons at the top of this window. The red line in the waveform window indicates the moment when the waveform was triggered. As per our settings, 12 of the cycles will be before the trigger occurred, and the remaining 3 cycles will be post-trigger data. Settings files. Settings files are a convenient way to store and edit offline settings for relays. Files can either be created using the Vista setup program, or settings already existing in a relay can be downloaded into a file. These settings can then be edited or simply uploaded back into a relay. To create a new settings file, select New Settings File from the File drop-down menu located at the top of the screen. This will open a window that will ask you to select the name for the file as well as a location to store it. You will also be asked to set the properties of the file. Select the button containing 3 dots to choose the name and location of the file. Enter a file name of Default and save the file. The software revision and installed options fields must now be entered before the settings file is created. These are called the file properties, and they must match the properties or options of the relay that the file will be downloaded to. If the software revision and options of the relay are unknown at the time of the file's creation, default properties can be used and then changed after the settings are complete and prior to downloading the settings to the relay. We will discuss how to change the property shortly, so for now we can use the defaults provided. Select OK to complete the default settings file. You will now see the name of our settings file appear in the file window on the lower left side of the screen. This settings file has been created with all of the default settings a relay would have when shipped from the factory. You can edit the settings of this file by simply selecting the file name and then using the Setpoints menu at the top of the screen to select the specific settings to be changed. Programming the settings of an offline file is performed exactly the same as when communicating to a relay. As mentioned earlier, existing settings can also be saved from a relay. To do this, establish communications with the relay by selecting the relay name, and then choose Read Settings from Device from the File drop-down menu. Once the setup program has read the device settings, you will be prompted to enter a file name. Enter the relay name and select Save. You will now see this settings file located in the file window below our default file. To edit the settings of this file, select the file name and then select the settings group you wish to edit from the settings menu. The properties of each of these files can be viewed and edited by selecting the name of the file and then choosing Properties from the File menu. This should be done prior to downloading any settings file to a relay, as the properties of a file must match the relay properties in order for the download to be successful. Let's download the default settings file that we created to the relay. We must first check the properties of the relay. To do this, we establish communications with the relay and then select Product Info from the Actual menu located at the top of the screen. We can see from the order code that this is a 745 W3 P5 G5 high ALR relay. The W3 P5 G5 indicates a 3-winding 745 with 5 amp phase and ground CTs. The high indicates a high voltage power supply is installed in the relay. The ALR represents the analog input-output, loss of life, and restricted ground fault options, all of which are installed. We can also see that the firmware revision is 2.8. This is all of the information we will need to properly set the properties of the settings file. We next need to compare the properties of our relay to those of the default settings file. Select the file name and then choose the properties from the file menu. We can see that the file was created for a 745 relay with firmware revision 4.0. The number of windings, control power, and ALR options all match our relay. However, the phase and ground CTs are set to 1 amp secondaries, as opposed to the 5 amps that are installed in our relays. Make the appropriate changes to the phase and ground CTs and select OK. You will be prompted that the conversion will overwrite the existing file. Select OK. To send the settings file to the relay, select the file name and then choose the Write Settings to Device option under the File menu. You will be prompted to select which device you wish to download the settings to. Highlight the name of our relay and select Send. The default settings will now be downloaded to the relay. Please note that settings files should never be downloaded to the relay if it is in service. Protection elements will not be able to function while the file is being programmed. Setpoint groups. There are 4 settings groups available in this relay. In some applications, changing loads or environmental conditions may require a change in the protection settings. The different settings groups allow 4 sets of protection elements to be programmed without changing any of the system or relay settings. Setpoint groups can either be programmed active in the settings files, or logic inputs can be used to automatically switch from one settings group to another. Select Elements and Setpoint Group from the Setpoint menu. The active Setpoint Group setting allows you to change which of the 4 setpoint groups is being used without asserting a logic input. This is generally left programmed as Group 1, and logic inputs are used to change the groups. The Edit Setpoint Group allows you to select which setting group you wish to program. The relay will still use the active group of settings for protection, but any setpoints viewed or altered using either the front display or the setup program will be from the Edit group. This is usually set to Active Group, but can be changed to allow programming of other groups. Change this setting to Group 2. When the Edit Setpoint Group is programmed different than the Active Setpoint Group, the LED for the Edit Group will flash on the front of the relay, while the Active Group LED will remain solid. If we now select the Winding 1 timed overcurrent protection that we have already programmed, we will see that all settings have been returned to their default values. This is because the previous programming was done in Setpoint Group 1. Any changes made at this point will only affect Setpoint Group 2. If we want to use a logic input to change from Setpoint Group 1 to Setpoint Group 2, we simply need to assign an Activate signal to the Group 2 settings. For example, if we assign Logic Input 5 to the Setpoint Group 2 Activate signal, anytime the Logic Input 5 closes, we will switch to the Group 2 protection settings. When programming of the second Setpoint Group is complete, go back to the Setpoint Group settings found under the Elements menu and return the Edit Setpoint Group to the Active Group setting. This will assure that the settings seen during any troubleshooting of the system match the settings that are being used to protect the system. Firmware Upgrades. Upgrades in firmware revisions allow enhancements in protection elements and operational performance of the relay. The Vista setup program has been designed to allow the firmware of the relay to be upgraded without requiring the relay to be returned to the factory. The latest revisions of firmware are always available on the GE Multilin website and can be downloaded free of charge. To upgrade the relay, simply establish communications with the relay using the setup program. Select the Communications drop-down menu located beside the Actual menu at the top of the screen. Click on Update Firmware. You may be prompted to close all device windows before proceeding. Select Yes. We will now be asked to make sure that the relay is out of service. All protection elements are lost when upgrading the firmware, so this operation should never be performed on a relay that is providing protection. Select Yes to proceed. The final prompt will be to make sure that the SR745 front port has been connected to the computer for the upgrade. Confirm that the connection has been made, and then select OK. You must now select the location where the firmware has been stored on your computer. The firmware file should be highlighted, and select Open. A window will appear indicating that the firmware is being uploaded to the device. This window will close, and the relay will reset when the firmware upload is complete. All settings within the relay will be lost when the firmware is upgraded. It is very important to save a copy of the settings file prior to upgrading the firmware. The file can then be downloaded back into the relay when the firmware upload is complete.